All right, so we've seen how if we're shown an acid, we can figure out what its base version would look like. If we're shown a base, we can figure out what its acid version would look like. Now we get one of each. This is a story where an acid meets a base, and when they meet, the acid says, "Hello there, would you like a hydrogen?" And the base says, "I would love a hydrogen." And we have to show what does the after picture look like? What does each of these things look like after a hydrogen has changed hands? So the HNO2 will lose a hydrogen, turning it into NO2, and don't forget the charge drops by one step. The bromine will gain a hydrogen, which turns it into HBr, and the charge there goes from -1 up to 0. Next one, C6H5COOH. This is not obvious, but I'll tell you now. When you have a compound with that generally will have some hydrogens in the middle and then a COOH on the end, this is called a carboxyl group, and we'll see more about them later. These are acidic, and the H on the end is normally the one that will break off. So leave these H's alone, take this one on the end. When this gives away a hydrogen, it should become C6H5COO, and the charge goes from 0 down to -1. That's benzoic acid. And the SO3, the base, gains a hydrogen and becomes HSO3, and charge goes from -2 up to -1. How do I know this is the base? It doesn't have any hydrogens, so it can't possibly give anything away. It can't be an acid. It's got to be the other thing. So it's a combination of that and seeing this carboxyl group and saying, whenever I see this, it's almost guaranteed to be a base, an acid, I'm sorry. Okay, here, OH is kind of the archetypal base, so this is definitely going to take a hydrogen, and this, HS, is capable of giving one. So if this gives away a hydrogen, we will get S2 minus, because that lost a hydrogen, its charge went down by 1, and the OH gained a hydrogen and became, you can write HOH if you want to, that's a valid way to write water, or if you write H2O, that's fine as well. Now, it is not obvious looking at this, it's not completely clear that this is the base and this is the acid unless you've had some practice. So if you looked at this one and said, maybe this will give away a hydrogen and this will take it, and we'll get H2S and an oxide ion. Later, after we introduce the acid-base table, we'll be able to show you why this is incorrect. But it's not crazy to think this way. And if you wrote this, do not feel bad. You followed a reasonable thought process, and we'll show you in a little while why this is not so. In general, you can expect whenever you see the hydroxide ion, it's going to be a base. It's one of the very strongest bases that exists. In this course, it pretty much is the strongest base that exists. Okay, enough about that. Can't possibly be an acid, no hydrogen, must be the acid. So HF gives away a hydrogen, becoming the fluoride ion, and this gains one hydrogen, becoming HS. Charge goes from -2 up to -1. Here's a carboxyl group again, so we know this is going to behave like an acid. This is ethanoic acid, or the stuff in vinegar. When this gives away a hydrogen, you'll get CH3COO minus and HNO2. Um, if you're looking this up, you might also find this listed as acetic acid. So, and then this would be the acetate ion. If you've learned that, that's not wrong either, but I'm trying to use ethanoic acid because that's going to tie into things we learned in Unit 3. Okay, last one. H3O is an acid. This is the hydronium ion, and if it gives away a single hydrogen, it drops down to H2O, and its charge goes from plus down to 0. And the ethanoate ion picks up a hydrogen and goes to CH3COOH. Could we put that hydrogen on the front and say HCH3COO? Yeah, you could, but that kind of identifies you as a person who slept through organic chemistry. We know that this is a carboxyl structure and that this H is attached to one of the oxygens, so it makes more sense to write it this way. Please do that. Good. See you next time.